Okay, so what we can break it is the second lecture of radiative processes, and we will continue where we left off. But now today we'll start off with one of the basic emission mechanisms that is actually very common both in terrestrial physics as well as in astrophysics. We're talking about black body dynamics. Now, people who have gone through bachelor's, so senior years of bachelor's, they must have gone through the statistical physics, right? Fermi-Dirac, Bose-Einstein. So, in that context, you must have already come across black body radiation, the definition of black body. So, I'm sure most, if not all, are familiar with this expression. How you derive it. You can derive it either the way the flat derived oscillators, strengths, or using this full-fledged machinery of statistical physics, counting the microstates, etc., etc. I will not go through that. I will assume that this is something that you get. But my intention in this lecture is to connect this that is derived from basic physics, connect it to intensity, and all the formalism we developed for radiative transfer. But before that, some of the basics, just to run through some of the basics again. So, the very basic definition of a black body. Black body radiation is when the radiation is in equilibrium with an object which has a finite temperature, a thermal object. So, radiation in thermal equilibrium with itself and a container, so an object. Usually, it is talked about in terms of a radiation, concentrated inside a container. But it can also be that radiation can be another object within the radiation field. Everything is in thermal equilibrium with each other. The key characteristic of a black body radiation is A, it is defined by a temperature with which it is in equilibrium with. And then also the fact that the radiation field does not change. So before it thermalizes, it interacts with the photons interact with the object. The photons can gain energy, photons can lose energy by increasing temperature of the object. In this way, after they thermalize, after the temperatures of the two fields equalize, it will not change further. So now, suppose we are looking at this container. Now, suppose we are looking at this container, and inside the container we draw a line, a ray of light. Now apply the radiative transfer equations. So from the basic definition of black body, this is 0 because the intensity is not changing. So the first basic principle that we have is the intensity of the black body, intensity in the way we have defined it, of the black body radiation field is constant. Intensity along any given ray through the black body radiation field is constant. Pi beta is constant. We will call that intensity the function B nu. We'll soon see how B nu is related to the energy density which you derive from statistical physics. Now, as soon as we have this B nu, Pi nu, if I just make you recall what we have done, Pi nu beta is 0, so I nu is constant. But on the right hand side, we have I nu equals to S from the right hand side. Which means the source function of a thermal object in equilibrium with a black body radiation field is constant. Okay, are you following the logic? I hope there is no questions. If there are any questions, please feel free to shout. Okay, so we will call that the S nu is the black body source function. Now, no matter what type of object it is, S nu is a ratio of the emission coefficient and the absorption coefficient. No matter what type of object it is, if it can come in equilibrium with a radiation field, that is, if it can be described as a thermal object, then its source function would be the black body radiation field. If it's not a thermal object, if it's a non-thermal distribution of particles, then it will not have this function. Prof. So that's a very characteristic definition of when can we call an object thermal object. We can call it when it is defined by a well-defined temperature. We can assign a temperature to the function. So a thermal object will have a source function equal to this. As soon as we have this, we can immediately find this principle. If the source function is a black body function, then the emission coefficient and absorption coefficient are related, they are not independent. So this is called the Kirchhoff's law. Again, I'm sure many of you have also gone through this. It's also taught in kinetic theory gases and basic thermodynamics as well. So what is the principle of Kirchhoff's law? Suppose you are inside this container which has a black body radiation field, and you keep an object inside the radiation field. Then the object is interacting with the radiation field, they're all in equilibrium. So the temperature of the black body is the same as the temperature of the object. Now I make a ray pass through the object. So suppose this is the radiation. You have the object. I'm not drawing the box. Now I have a ray passing through it. Outside the object, the ray has some intensity. Now, by our definition, the d angle term is 0 because the black body radiation field is not changing. Within this object, then also the intensity cannot change. So if there is some emission coming from the object, that will have to be counterbalanced by the absorption from the object. That is what this Kirchhoff's law is telling you. That no net radiation is either subtracted or added to the ray as it passes through the object. Okay? Then I'm sure you've all heard of this as well, Stefan's law. You have heard of it? Any questions? You have heard about it in a different context. The total flux and the luminosity is proportional to T to the power 4 to the constant sigma. This actually has a more fundamental form, which is related to the energy density. U, small u is energy density, and this you can derive from the basic laws of thermodynamics itself. I've sketched the derivation here. Just briefly go through it. So this is the first law. Okay. PdS is equals to du plus pdV for a region confined within a volume V, and assuming that the region is black body radiation. Now, U is the total energy. So, in terms of our small u, which is the energy density, the capital U would be small u times the volume. Okay. Pressure of a radiation field is energy density by 3. Okay. This you have to see how you derive it. And take this as an exercise. So then let us compute the first term here, Tu. Tu, just a chain rule of the derivatives. I've added a dt on both sides. Essentially, it will be d small uv and u small dv. I've made it a derivative of dt. So du dt, v dt. I'll use this into here and also use the fact that p equals to u by 3. So I have a u dt here. I have a u by 3 here. Everything will join up to the 4 by 3 u. It is very trivial. You can actually just note down this, and then derive it yourself. So this is the starting form, and this ds, the entropy, is a perfect differential. So what we'll assume is this second derivatives are equal. Right? So once we do that, then this is del S del T. I have a derivative of with the volume V. For this term, I'll have a derivative with the temperature. So this term, volume V, just so simple, du by T, 1 by T du T. This term, just 2 more steps, will give you minus 1 by T square, and then du T. You join everything together, you'll find that you get u equals to 8 e to the power 4. Again, it is very basic algebra. There's no need to go to the board for this. But if you just take this as an exercise, that starting from the first law, use this and use the fact that it's a perfect differential, you'll come to this. You can even take this as an exercise. So this tells you that the energy density of a radiation field which is characterized by a black body radiation, is equals to some constant. A's in the textbooks are known as the radiation constant. It is about 4. Okay. Now let us go to the Stefan's law. So you've seen this, use the total energy density. Now U is the total energy density, which is integrated over all solid angles and frequency. Now let us go once again to the definition of U and I. So there was one small typo in my slides yesterday. Here I had forgotten to give the C in the denominator, it will be I minus C. So this U omega d omega equals to I U by C d omega. So this U that we are talking about, this is integrated over the solid angle. So U omega d omega is a solid angle distribution of the energy density. You integrate over the solid angles. Now you also integrate over all frequencies. That is the U we are talking about right now. So just to make you know, this U nu, we found that it's equal for an isotropic radiation, which is also the case for the black body radiation field. It is 4 pi by C capital J. Okay. So then, since it's isotropic, so I nu is the same as J. J nu is the solid angle average of I nu. It's the same as J nu. It's the same as the black body radiation. So we just use this function, and then we had the U nu equals to 4 pi by C J nu. And we just have to integrate over the frequency. Just using the results from the previous lecture. So V nu is the solid is the frequency dependent form of the black body function. This is the integrated form, which is V is just a function of temperature. 4 pi by C V. Okay. So now we have a nice relation between the black body radiation intensity of the black body radiation field and the temperature. What does it depend on? Speed of light, the radiation constant, and 4 pi. Now also recap that when we had done this exercise of a uniform sphere with the intensity constant on the surface of the sphere, and then found that the radiation at a far point on the sphere falls over 1 by r squared. But on the surface of the sphere, it is pi times the intensity. Okay. Now, inside the black body radiation field, we can always draw any given sphere. And since because of the assumptions of isotropy, etc., the intensity on the surface of the sphere is on constant. So the flux from any body that is in equilibrium with the black body radiation field is pi times p. So now you have the Stefan's law, which is the flux from an object which is in thermal equilibrium with a black body radiation field, or which is giving out black body field, is sigma times k to the power 4. So the Stefan's constant sigma is nothing but the radiation constant C by 4 times a factor B, so AC by 4. Okay, so this is the Stefan's law. So now we always use this for finding what is the luminosity of an object, what is the total radiation coming out from the sun. For example, assuming the sun is a black body. All these games we play. Okay. So as I said, this is the energy density of a black body radiation. How do you find it? You use the basic principles of Bose-Einstein statistics, count the number of microstates, normalize things, you get this expression. Let's not go into that for now. We'll take half a lecture to derive all of this. But what is important for us is, this is the energy density as a function of the solid angle. Now, U omega is I nu by C, but I is black body. So we directly have an expression for the black body intensity function. This is the energy density of the black body radiation field. This is not much of use when you do radiative transfer. This is the function that we have to use when you do radiative transfer. When you see the spectrum of a black body radiation field, this is the form that we have to use. So 2h nu cube by c square and an exponential minus 1. I'm sure again many of you have gone through what is the nature of the functional form, how does it look like. But I must stress that this is somewhere the students make a lot of mistakes. Firstly, many are not very comfortable to draw the how the function looks like. Okay, I have to figure in the next slide, but I'm tempted to see if anyone can remember or guess how the function would look like. Anybody wants to try? Any of you remember how it looks like? You can sketch in your notebook as well if you want to. How would this look? You can take the y-axis as log and the x-axis as log of frequency as well. So make it easier. Remember, it has a power law in the numerator and exponential in the denominator. I'll give you guys 2 minutes. You can also take the hints that I've given here. What happens in the low frequency limit and what happens in the high frequency limit. Calculating. They're not done. Okay. Okay. Hold on to it. On the axis. We started with the axis. You can look at the limit forms I have given you on the slides at the bottom. Fortunately, I don't have time for tutorials because I have behind a bit differently. So let us try to see, before I even go to the next slide, let us try to see how to draw this. So suppose this is log ln. Okay. So you can see that in the low frequency limit, the exponential can be dropped off. Exponential's contribution is very small. So, or not, it's very small. You can expand the exponential in powers of h nu by kt. The 1 will cancel from the denominator. You'll get h nu by kt in the denominator. So then that gives you 2 mu squared by c squared kt. So if I'm drawing a log plot, how would that look like? Huh? Straight line. Good. Something like this. Right? Now, suppose I'm starting to get near kt. This point is equals to mu kt. It's not exactly mu because I'm plotting log mu. So what happens then? You have a power law with an exponential. What will happen to the power law? You see, the nature of the power law is same. 2 mu square by c square. Okay? But now there is an exponential negative exponentially. So now if h nu is larger than kt, which of these two terms will dominate? Exponential will dominate. That's right. So then this formula will start to bend. It's like exponential function. Okay? Good. This is how a black body function looks like for a given temperature. One second, my students are giving messages on Slack. This is for one temperature. What will happen if I increase the temperature? Speak up, speak up. What do you think will happen?
All the intensity would rise and the peak would shift.
Peak would shift. In which direction? Left or right?
Higher frequency.
Higher frequency. So is this a valid curve? Will it be like this? What is wrong with it? Huh? It should have a lower energy. No, but KT is proportional to mu, so if KT is rising, then mu is also rising. This is correct. To shift to higher. But why is this wrong? It can't? It can't intersect. Why can't it intersect?
Can't have two temperatures.
Perfect. Yes. Very good. This is how it looks like. For higher and higher temperature, the peak shifts like this. This is a black body in the frequency space. You should figure out how the black body function gets in the wavelength space. Okay. But before that, just to give you a bit more information about these two limits that I was talking about. So for frequencies much lower than the KT, we have a linear relation. Not a linear relation, but linear in the log space. So that is called the Rayleigh-Jeans split. Again, I'm sure many of you have already gone through this. So in the Rayleigh-Jeans limit, the black body radiation function is equal to 2 mu square by c square times kt. For the higher frequency, when the frequency is much larger than the temperature of the object, then you have this exponential damping for the wavelength. So these parts. So the turnover happens close to kt. So below the turnover, it is Rayleigh-Jeans. Beyond the turnover, you have a wavelength. Rayleigh-Jeans is very useful in radio astronomy because radio waves have larger wavelengths, so smaller frequencies, and the typical temperatures of the objects that we are seeing, of the black body objects that we are seeing, are such that the wavelengths are much larger. So h nu by kt is usually less than 1. So in radio contact, let me see if I have defined it. No, I don't discuss brightness temperature. I guess this will be taught to you when somebody discusses radio astronomy. But in radio astronomy, you can see for a black body radiation field, the radiation field is directly proportional to the temperature of the radiation field. Now, people often use this concept as a proxy to characterize the emission coming from any object, whether it's thermal or non-thermal. You get the spectrum. Spectrum means you are measuring the intensity that is coming towards you. And you just use this formula blindly to assign a temperature to that field. So that is called a brightness temperature. Now, if the radiation is truly from a black body, then the brightness temperature corresponds to the thermal temperature of the object. If it is not a black body, it is just an empirical qualifier for the radiation field. So, in many of the cases, for example, for non-thermal radiation, let's say I will discuss synchrotron radiation. Synchrotron radiation coming from relativistic electrons gyrating along a magnetic field. If you look at the temperature distribution of those objects, for example, jets coming from supermassive black holes, the brightness temperature would be in the order of 10.12 or 13. These are called blazars, so the jets are directly pointing towards. Now, if you do not know anything about the source, just the basic fact that the temperature is so high, the brightness temperature is so high, will tell you that this is not a black body radiation field, because having such a high temperature, an exotic object, will completely is sort of unrealistic. If you look at the emission coming from gas in the ice and in the galaxies, you often find that the brightness temperature is order of 10,000 Kelvin. Now, if you work out the ionization and photoionization equilibrium balance of the gas and galaxies, you'll find that the temperature of a photoionized gas is also equivalent to 10,000. So in that case, the brightness temperature is indeed close to a black body radiation. So even from the very basic first observation itself, you can understand something about the nature of the source. Why quantify what is the brightness temperature? So that is one use of this form. Where do we see the wane limit? If you look at very high energies, for example, now you are going to X-ray astronomy or gamma ray astronomy, then this exponential cutoff becomes important. So for example, the hot gas surrounding the disk of gas falling inside a black hole, that's called the corona. You find the coronal temperature, and also you can see some emission from the thermal radiation from the gas falling inside black hole. So it's called an accretion disk. It forms as a disk, goes inside the black hole, and the thermal gas in the disk gives rise to disk black body emission. So if you look at that distribution, so the total spectrum will of course be a convolution of all different components. So the hot corona will give you content emission, the disk black body will give you some black body emission, etc., etc. But if you plot the spectrum in those cases, you'll find that the disk black body spectrum will cut off beyond a certain frequency, cut off beyond the temperature of the gas. It's not a single temperature, there's multicolored black body, the different temperatures and different grains and accretion disk. But there you will find that the spectrum actually looks like this. So this is where in high energy astrophysics, the wane limit becomes important. Oh, and another important one is the peak of the black body distribution. Del mu. If you work this out, you will find, and it will not be an analytical solution if you solve this numerically. You will find this gives you h nu equals to 2.2 kT. This, in many textbooks, are known as a Wayne's displacement law, which means that if you find the peak of the black body distribution, you can relate it to the temperature of the black body. Interestingly, if you work out the same formula in the wavelength space, the coefficient in front will be different. So the temperature you would infer just by finding the wavelength will also be different. What it means is the shape of the, because you'll find that when you work out the temperature, there will be, this is black body times d nu. The total emission is u nu times d nu. This d nu will give you 1 by lambda square when you work in the wavelength space. So you have additional lambda factors that is coming. So Wayne's displacement law is not a fundamental law of nature. It is just a proxy to calculate the maximum temperature of the maximum of the radiation spectrum. And it's just an empirical formula that relate the peak of the curve to the temperature.
So mu max does not correspond to
lambda max,
not by C max.
Not like that. Yes. So if you look at the same distribution in lambda space, lambda max will differ from max. One of the most well-known black body spectrum, I'm not sure how many of you were there for the looking yesterday, is a cosmic microwave black body. Black body radiation due to the photons that have decoupled from the matter many years ago. And it perfectly fits the black body. So, here are the units. Yeah, so they must have, yeah, you have to tell George Smoke, because this is a Nobel Prize winning paper. They must have made a error there. So this will be lambda, yes. Maybe he has switched the locations of lambda and frequency. Okay, so far about, I'll stop here for the black body radiation. Next, I will go to Einstein coefficients. Has anybody heard of what are the Einstein coefficients? Yeah, it has been taught in the covered limits. Okay. So you're all already aware of it, so I don't have to spend too much of time. So you all know that Einstein got Nobel Prize for this. Spontaneous emission, absorption, and stimulated emission. What we'll learn here in this case, how do you relate all of this to, again, the basic formalism of radiative transfer. That is what our aim is, not the basic physics, but connecting it to the radiative transfer equations. The spontaneous emission, the probability that any atom, let's say, where the electron is in state 2 will make a spontaneous transition to the state 1, A2 to 1. So that's the coefficient of spontaneous emission. Absorption, electron in state 1 will interact with the incident photon, get energized, and go to state 2. The probability of that happening is a coefficient V12 times the incident radiation field, J bar. Now, there is something different about the notations I'm using right now. What I'm using is this something called the line profile function, finally. Because you see, J nu, which is the incident radiation, can have any arbitrary distribution in terms of the spectrum. But this transition will only happen over a small range of wavelengths. So to be exactly true, this will only be at h nu. As we know, frequency is not exactly, cannot be measured. The energy due to the uncertainty principle cannot be exactly measured. So that is this why this gives rise to this profile function. So H profile function usually looks like a Lorentzian function. And in practice, sharply peaked like this. Centered about the nu naught, which is the transition frequency. Okay? And this the profile function integrated just over itself, so this is 1. The profile function is usually defined in this space, but it's normalized 1. So as you can see, the profile function almost acts like a filter. It filters out the incident spectrum to only lie around the transition frequency. And this we are calling it J bar. And J nu is the isotropic distribution of the incident radiation field, and finally V nu is 1. Good. So the absorption, of course, as we have done in the previous lecture, will depend on what if there's an incident radiation field, a fraction of it will get absorbed. So that is why the probability of it is also proportional to the strength of the incident radiation. Now, stimulated emission. Just like incident radiation, if a photon feels, if an electron in the state 2 feels an incident radiation field, there's also a probability of it transitioning from 2 to 1. This is called stimulated emission. Stimulated because the photon is interacting with the electron and stimulates the electron to make the transition. So this is B21, this is B12. The functional forms of these two probabilities are same. This is a new term that Einstein had included. If you do not include this in your transfer equations, then you do not get the full Planck's equation. You just get the Rayleigh-Jeans term. You can actually work this out. It's an interesting exercises for you. But we will include this for now. So for thermodynamic equilibrium, so if the radiation is in equilibrium with the thermal object, which is the basic definition of a black body radiation field, then total downward transitions should match the upward transitions. So B12, 1 to 2, that is an upward transition, is equals to the number density in the state 2 times A to 1, spontaneous transition, and number density in the state 2 times the stimulated emission. Do note that the number densities on the right hand side and left hand side are different because the composition of the object with the electrons in state 1 will, that is the n1 number of particles have this state, whereas electrons in state 2, n2 particles have this state. per unit volume. If you work out just rearrange the terms to express the J bar, which is the incident intensity of the radiation field, you get something like this. Okay. So the numerator is a ratio of the spontaneous emission and the stimulated emission, and the denominator is a ratio of these two coefficients N1 and N2, the densities, number densities, and again the ratios of the stimulated and the absorbing coefficients. Now from thermodynamic equilibrium, basic statistical physics, the ratios of these two states can be the number densities of the in these two states can be written as G1 exponential minus EKT. I'm just removing the normalization. And N2 has a higher energy, right? So E plus H2. E is the ground state energy. Ground state that is the state with energy, energy of the state 1. It may not be the ground state. So if you just work it out, you get the ratios of these degeneracies, G1 and G2, and exponential H2 by K. Okay? Degeneracy is the spin degeneracies, which you learn through the quantum mechanics. Sure. So for simple hydrogen, for example, just two spin states. So this is the functional form you get just from basic assumptions of how the spontaneous emission, the absorption and stimulated emission take place. And if the total upward transitions and downward transitions are in balance. So it means that total absorption and emission by that object is in balance. This is again the basic definition of black body radiation. Now compare this with the Planck's formula or the black body radiation field formula. You will find that A21 by B21 would be the ratio of this two should be 2h mu cube by c square. And the ratio of this should be 1 because we did not have any coefficient in front of exponential h by k. So now we have derived this independently. We are using some extra input from the black body radiation field, which comes again from the Bose-Einstein statistics, to make a relation between these three. So what does this tell us? It's a very powerful relation. It's called the Einstein relation. If experimentally you can determine any one of these, all the others would be determined. For example, if you find the spontaneous emission coefficient, you get B21, you get D21, you get B12. Okay, so you have to just find out one of these, and all the others will be defined. Why is this important? Because this gives you the microphysical description of how the emission coefficient and the absorption coefficient looks like. So in terms of the emission coefficient, the J nu that we had defined, which is the emission per unit volume, per unit solid angle, per unit frequency, etc. This looks like the total number of such elements, N2, number density. H nu naught is the transition frequency, that's the energy, divided by 4 pi because this is per unit solid angle, and then A21 is the finding, is the profile function, which is the emitted photon at H defined. Now the absorption coefficient. Again, similar game. We find the total probability divided by the solid angle, multiplied by volume, time, H nu, etc., etc. You will work this out. You'll find that your absorption coefficient, I'm just going a bit fast here because again it's just repeating the same arguments. The absorption coefficients will also depend on H nu by 4 pi and 1b12 pi. Now this is very powerful. Why? Because now you are relating the emission coefficient and absorption coefficient to some fundamental properties of the system itself. If you know the number density, distribution of the number density of the particles of the states, and if you know one of these Einstein coefficients, you can find what the absorption coefficient would look like. If you have this, you can find what the emission coefficient would look like because if it's a thermal object anyway. So if you from the microscopic physics, if you find any one of these, and if it's a thermal object, you can quickly find the other objects, other coefficients there. Now we'll just rearrange these terms in terms of another concept that one has to keep in mind is for the stimulated emission, we can treat it as negative absorption. Fine. Go back to this figure. V12 is the absorption. Right? Going from state 1 to state 2. That is proportional to the incident radiation field. The stimulated emission, if we just take it to the other side, the functional form looks like this. So to treat it mathematically, it is much easier to treat the stimulated emission as a negative absorption. So once you have the Einstein absorption coefficient in terms of the Einstein coefficient for absorption, the stimulated emission will just look exactly like this, but with N2 instead of N1 and a negative sign. So the total absorption of a system is often defined in this way. Okay. And again, all of these are derived in more detail in Riviki and Lightman. I unfortunately have a limited amount of time, so I can't go into all detail. But you're welcome to look into these details if you want to. But what is important is to understand some of these basic concepts, that there is stimulated emission, there's absorption, and there's spontaneous emission. All of these you can relate to the microphysical properties to get the quantities we've defined for radiative transfer, which is the J nu and the alpha nu. Because now you can understand that we can quickly write down the radiative transfer equation of a ray passing through an object. And if we know the microphysical properties of the object in terms of the distribution of the number densities of the atoms in the state 2 and number densities of atoms in state 1, we can quickly compute what is the absorption coefficient, the emission coefficient, etc. And inside the absorption coefficient, we treat the stimulated emission as a negative term. Okay, now we'll just use the relations of the Einstein coefficients to make the absorption coefficient look like this. So far, we've just used the Einstein relation. If we now impose that this is in thermal equilibrium, then we can just use whatever we've derived earlier. N1 by N2 and equals to G1 by G2 exponential H2 by K2. We can just write it here. So N G1 N2 and G2 N1 will be exponential minus H2 by K2. So now you have a working functional form of the absorption coefficient of a system. You have a working functional form for the emission coefficient, you have a working functional form for the absorption coefficient. The only unknowns are the V12 and K21. This you have to define it from elsewhere, from experiments. This form of the absorption coefficient is called LTE, or in the approximation of LTE, or local thermal equilibrium. Okay, in the last few minutes, I'll talk about the nature of the spectrum, of the spectral line. So we talked about emission and absorption. So these, if it's emitting, you'll see a spike in the spectrum, corresponding to the frequency at which the emission is taking place. If it's absorbing, you'll see a dip in the spectrum, corresponding to the frequency at which the absorption is taking place. So you would naturally expect that the emission and absorption would be just at a single frequency. But if I again go back to my initial slide, this one for example, you can see this is not a delta function. There's a wide range there. So this range can happen because of many different possibilities which I will discuss right now. So one, of course, you can understand is because of the quantum mechanical nature of the system. Energy is not finite, cannot be found accurate. So there is an inherent width in due to the uncertainty in the frequency itself. So that is called natural Broadway. I'm sure again many of you must have also been exposed to this concept. Let's see if you have gone through the mathematical derivations of many of these things. So this is called a quantum mechanical problem, and this usually looks like a Lorentzian function. So for more reference, you can look up this book, Theoretical Astrophysics, Volume 1, by Kanu Padmanabhan, and Chapter 7 of this book. It's a very nice book, by the way. And with a lot of details on many different objects, but in Chapter 7, he works out the nature of the problem. Fine, so this is the quantum mechanical problem. It's a Lorentzian function. You can say it is omega minus omega 1, 2, which is the transition frequency, plus this gamma by 2 square, where the gamma is the spontaneous decay rate related to the A21. Okay, so this is actually very small. Unless you completely shut down all the other broadening mechanisms, you normally would not feel this too much. The next is called thermal broadening, or Doppler width. It's also sometimes called known as a thermal broadening resistance, or pressure broadening. So what is happening is the atoms that are emitting the radiation, they are not static. If it's a thermal gas, they'll follow a distribution function. They'll follow the Maxwell-Boltzmann distribution function. So if they have a distribution in velocity, at the rest frame of the atom, the emission is at mu naught. But as soon as you go to the lab frame, then you have a Doppler shift of the frequency of the photon. This is the Doppler formula. So just rewrite it. You can relate the velocity with the delta omega. Fine. So this is how the distribution of the atoms in one particular direction looks like. Why are we considering unidirectional Maxwell-Boltzmann distribution? Because we are looking along one line of sight. We are not going the volume now. So this is a 1D Maxwellian gas for our purpose, as we are looking at through the ray coming through a gas, or the emission coming through the gas along a particular ray. So this is MIVZ minus capital V is the mean velocity of this distribution by 280. Substitute this factors here, you will get omega minus omega bar whole square. Omega bar is related to the mean, the central frequency. If there is no bulk velocity, then the omega bar is the omega naught. Okay. If there is a bulk velocity of the gas is then that will also give rise to a Doppler shift. So the omega bar will be Doppler shifted form of the omega 0, Doppler shifted by capital V, which is the bulk velocity. You understand what is the difference between bulk velocity and random motions. The gas is static, it is not moving with respect to you, but the atoms are moving. But the gas itself is moving, the center of mass velocity of the object, as well as the random motions of the atoms around the center of mass. Okay, so if you work all this out, you'll find that the probability distribution is an exponential function, a Gaussian function. Omega minus omega bar whole square divided by the width, but this width is related to the temperature. This delta omega squared, the delta omega is 2 kT per inch squared. So this now gives you, so this one was giving you a Lorentzian function. This gives you a Gaussian function. This is very often mostly seen in situations where the temperatures are high, gas is thermal, and it is not polar, so the densities are low, so the collisional broadening is not. So collisional broadening will come to the next time. But the collisional broadening is not is less significant compared to thermal broadening. So the lines look like Gaussian. So in many of the standard astronomical tricks, we start off by trying to fit Gaussian profiles. It's an approximation because the other broadening will also be used. To be exactly accurate, you have to use a convolution of different functions. You have to use a Lorentzian function as well as a Gaussian function. I'll come to that. That's called a void function. Now the last broadening term. This is called collisional broadening. So the electric field that is coming out of an atom, let's say. So now I'm going from discrete energies to an electric field of the radiation. So the wave particle duality. So if you are seeing electromagnetic radiation, it is oscillating as a sinusoid. But then it is a finite lifetime because the object will not stay there for a long time because it's actually a pulse. You have a finite transition, you get a emission only for a certain duration. So there's a decay rate, the decay lifetime associated with that transition. That is related to this gamma t by 2. This is some normalization, let's say. Gamma is again the spontaneous decay rate. So if you are trying to find out what is the nature or what is the functional form of the electromagnetic radiation due to this transition, it will be a sine wave modulated by this decay rate. And then another function that defines the phase of the radiation. Phase will also depend on the time. Because after one transition, if you get the transition from the next atom at the same phase, so the same atom after it again makes a transition to the higher state, the same phase, then that becomes correlated, stimulated emission. But in a generalized system, the phases will not match. So you have a separate function for phi, which is a dependent on time. Okay. So the last, this term is actually can be modulated by collisions with objects. So if you have these atoms moving about, they can also collide. And as they collide, the phase will change. So this is what will take care of the change in phase due to collisions. So if for two transitions, if there are no collisions, then the phase remains unchanged. It's an undisturbed system. So this average between the two phase functions is 1. If there are collisions, then the average is 0. What is the probability for 0 collision? Now the collision is a Poissonian process. The Poissonian probability distribution, if you have the probability for n occurrence, is x to the power n minus x by n factorial. For 0, it is just exponential. This collision frequency u1 minus t2. Mu c is the collision frequency. So then, what we can understand what we have to do now. We have to take an average of this quantity, assuming that we have no collisions taking place. So we transform this into the spectral domain. Why spectral domain? I think I will discuss it in the next lecture. If you want to find the spectrum of an electromagnetic radiation field, you can take a Fourier transform of it, and square of the Fourier transform gives you the spectrum. So E, due to a moving charge, you get some radiation, some variation in the electromagnetic field, but the spectrum of the electromagnetic field is related to its Fourier domain, the Fourier form of the electromagnetic field. So mod E omega square, E square, and you take a average of this. The integral is a bit complicated. I will not discuss it. I'm not sure if this are the lecturers putting up the lecture slides anywhere. Has this been told to any of you?
They are sending it to us.
But they are sending it to you. Okay, so I'll send these slides to the name so you can have a look at it. So I'll not discuss the full integrals here, but just to give you a flavor of how you go about it. You can see this stochastic term, I will separate out. The rest of it is just integrals over the time. So you can see this is over one time t1, this is over time t2. So I have missed the t1s and t2s. If you add everything together, then this will look like this. And the stochastic term, we'll take the stochastic term to be 1, assuming there is no collision. You work out all the integral, and you can find the final integral in this Wolfram website. You'll find it again looks like a Lorentzian term. Okay? Centered about omega naught, but the width of the Lorentzian has both the spontaneous coefficient plus the collision term. So earlier in the spontaneous coefficient, spontaneous transition, we just had gamma by 2. Now, as we use this probability distribution here, that the probability for this to happen is exponential minus mu c t1 minus t2, and another collision term has been added. So width of this line, of this Lorentzian, is actually related to the collision frequency. How do you find the collision frequency? If you find what is the mean free path, what is the density of the object, and find the collision frequency. So this now becomes a function of the density of the object. So thermal broadening, function of the temperature of the object. Collisional broadening is function of the density of the object. As you can understand, in a realistic system, both of this will contribute. So to fit line profiles, I'm sure you'll hear about it in some of the observation-based lectures. You'll actually have a formed like this, where you have a Lorentzian and an Maxwellian. Put everything together, normalize things, is something called a white profile. The G is silent. It looks like a Gaussian on the top and the Lorentzian in the denominator. That white profile is actually not so simple to work with, but you can write up codes and then to fit the white profile. As you can see, this coefficients of the white profile are both related to the collision frequency, which is related to the densities and the temperature. Okay, so take away message before I end the lecture. We learned about black body radiation field. We learned what is the intensity of a black body radiation, how it is related to the coefficients of radiation transfer. We learned about the microphysical transition rates. We learned about the Einstein coefficients and how all of these combine to give you the basic coefficients we need for radiation transfer, emission coefficient and absorption coefficient. We also learned about the fact that there are emission lines. This is also true for absorption lines. I'm talking about emission, but the other also works. Because if your photons are getting absorbed by particles moving about, the absorption will not happen at the frequency of the absorption, but will differ because of the Doppler shifts as well as the collision. So if you have lines, emission and absorption, they will be broadened. They will be centered above the basic frequency unless there is some bulk velocity of the absorbing or emitting object. They are centered above the basic transition frequency, but they have a width. And the width is related to both the temperature of the object and the density of the object. Okay? So we'll meet on Monday again. Then we'll discuss some basic properties of electromagnetic fields. Let's see what do I have in store for this. Okay. The moving charges, distributions, etc. So we'll slowly go towards synchrotron radiation in the next lecture. Okay. Any questions?
Basically, why is the coefficient broadening the light? Like you showed the Fourier transform is making it blurred, but like what is the
it changes the rate. It changes the lifetime of the emission. So the physical process is same as the fact that if you have spontaneous transition, if you have radiation coming out, then there's a finite lifetime of the radiation. So if you convert, so if you not have a finite lifetime, if you take a sine wave, take a Fourier transform of it, it's a delta function. If you have a finite lifetime, that delta function will then be modified by a sinusoidal Green's function. So that gives you, as I said, I'll show you in the next lecture why the electric field is related, the spectrum of the electric field is related to the Fourier transform of the electric field. Take the Fourier transform, that finite lifetime gives you the fact that it is not a sinusoid also. And if it's not a sinusoid, then there's a spread of frequencies which are different. Time for tea break.
How can someone like finding out the study but actually input the thought electronics which one yeah in these yes we have
Right?
actually science something like this.
Can you one
I don't want it's okay to become outside. So okay then. Come outside. We had like almost half an hour. It's 10:30.
Then you can go slower, man.
Harshada, you're from Tamil Nadu, You're from Tamil Nadu?
Yeah,
So you know Tamil?
I can understand.
You can understand.
And speak, but I'm not very good. I just
I think Tamil Nadu.
no,
When I was preparing for the test and all that, then I did the text for ED and like I optics. I don't know exactly, but because it's no. Actually, I did the text for my paper for India. I didn't read it properly. Like I read in 2022. I gave interview for ICTS and paper company and didn't able to clear both. So it's okay. Doesn't matter now.
something or they give something they teach nothing and they give something else and forever. You come understand. At 6:45 very big. Type of income. I will have let her know what I'm interested in. चेंज करके चेंज किया तो वो चेंज करके सेव का नाम अलग ये तो और है No, I got confused with the name. I was seeing his lecture and I for that name. No,